All right, I think we can get started. So, hey everyone. So this is going to be like another machine learning like short stream. And basically like a lot of applied machine learning sort of boils down to like a bag of tricks. So some sort of best practices that people in the community know about to get models to converge faster and more cheaply. And one big trick that I've been using a lot recently has been mixed precision, and it's just like so absolutely useful and easy to use that I thought I needed to make a video about it. So as a use case, like we're going to look at this code base that I've been working with on UNet. So UNet is an image segmentation model, and basically, like given an image that looks like this, you're going to try and predict where the object is via like a segmentation mechanism that sort of looks like this, right? And so the main way this really works right now is basically if you want to turn this to mixed precision, you're going to have some images and you're going to have some masks. And basically, initially, let's say these are float 32s. You would just say, I want to make these torch halves. You know, and that's pretty much it. So there's that. And then the other change you need to make that doesn't show up here is you also need to make the weights of the network itself like precision half. And that's pretty much it. Like there's some subtleties involved that I'll go over next. So let's talk in a bit more detail, like what's going on here. So when you say like floating point precision, typically, like let's say this is a float 32, for example, like you'll have 8 bits dedicated to the exponent and 23 bits dedicated to the fraction. So this is really important, like when you think of something like scientific computing, where like the measurement error is really important, like you need to be able to be really precise. But in machine learning, typically we don't really care. We just want to have like a large range of values. And so typically, like half precision will look something like this. Like you still have 10 bits, like you still have double the bits for the fraction than you do for the exponent. But that's pretty much it. Like, and you need to sort of make sure that you have like fast adders for this in hardware, and adders give you multiplication. But otherwise, like that's pretty much it. So you may ask, like, well, why 5? Why not 10? Like, why not, have 3, or, give 10 exponent, or like, I don't know, 8 fraction? Like, why did we decide to split it up in this way? Well, like a quick answer to that is that you don't have to. And so in fact, like Google, for instance, has like this paper on bfloat. And so for example, like in bfloat's case here, you'll notice that in half precision, like they have more bits for the mantissa. So as in like the precision. Oh, hey, Krishan, nice to see you on stream. So this is going to be a quick stream, so I'm not going to be taking too much questions except till the end. Whereas like bfloat is basically going to be you're going to have like more in the exponent, so it's more expressive. And so it turns out this also lets you train models just as fine as float 32, even though you're using half the amount of memory. So what is really like the whole benefit of mixed precision? Like really, there's sort of two main benefits in here. So this is like NVIDIA's page on mixed precision, and I thought it was a really great summary. So the first one is like the obvious one is that, well, if a model takes half the amount of memory, then you can train it faster, and you need half the amount of memory to be able to store it. And so as a result, you can have models that are like twice as big that you can work with. So basically, model size is a proxy for the amount of training time you're going to run into. So this is just so important. Like whenever we're dealing with these absolutely gigantic models, it ends up becoming a very useful trick. And even for non-gigantic models, I would say it's a very useful trick. So it doesn't really even stop at floating point 32. You could have like, I don't know, floating the int 4 or int 1. And so there's all sorts of research trying to get this, trying to get the precision. So trying to get the floating point as small as possible. So you just need to check for yourself, like try them all out and see what's the best for you. That said, NVIDIA has like these new tensor cores and their new Volta architecture that makes it especially fast to run floating point 16 matrix multiplications with an addition. So you can think of this as, you're multiplying two matrices and you're adding some bias, right? So this is like the typical logistic regression scenario, like where like a single layer neural network. And so it's sort of like highly optimized for this case. And so, like I said, like the main thing that you really need to worry about, like when you're programming this stuff, is that you need to make sure that like your model weights are half, and that you need to make sure that your inputs are like also half. But then there's still a subtle thing that you need to do here. So let's talk about something like batch norm. So typically in batch normalization, you want to make sure that like the outputs at in any individual layer isn't too big or too small. So what you would do is after giving it a whole batch, you want to make sure that throughout the whole batch, they have a like the whole batch, the activations have a mean of 0 and a variance of 1. So very similarly to how we do pre-processing for regular, logistic regression, which is a single layer neural network, you would do this pre-processing on the input. So people had a suspicion that this would make like models generalize in a more stable way and more quickly uh, for deeper networks, and it indeed does. But there's a subtle thing that happens with batch norm. So let's say you're aggregating a whole bunch of weights, right? And so you have like all of these activations for all your individual inputs for a given batch. And now you're casting them to a floating point 16. Well, you're just going to lose a lot of information because the contribution of any individual example is going to be very small. And so what people do here is they actually maintain a copy of the weights in floating point 32. And then they copy these weights to floating point 16. They do forward prop with a floating point 16. Uh, and then they multiply this by some sort of scaling factor, do the back prop, and then multiply back the weight gradient by 1 over that scaling factor. So loss scaling, basically, you don't always need it, but you certainly know that you do need it when, after training a model with mixed precision, you see nans everywhere. That typically means that you need to do loss scaling. So this is like I just showed you now how to do it like how to do it like manually, but you can also do it automatically. NVIDIA has a product called Automatic Mixed Precision, and basically here it shows like how you do it here. Like let's say for example, this is an example in TensorFlow where you have your optimizer, and then for your optimizer you enable mixed precision, and that's it. So this would automatically do the loss rescaling for you, the casting of the inputs, the casting of the model. So you don't really need to worry about it. So in terms of success stories, you see like the numbers that NVIDIA are reporting are really impressive. Like just this like 3-line code change is giving them 3.3x speedups, 2x speedups, 2.6, 2.5. I myself have generally seen about 40% speedups on the models that I've ran, but that could also be due to me not optimizing them enough, me not like, doing more hyperparameter tuning to really get it to work. But at the very least, like just not doing anything, like just taking the exact same model and doing it, if that gives me a 40% throughput improvement, like that's huge, and there's no reason for me not to use it. And so, for example, here I was talking about like, well, NVIDIA specifically has like these tensor cores that make it very easy to multiply two 4x4 floating point 16 matrices, and then adding one with a fused matrix multiply. So this operation is called the mul-add, where you multiply then add. It shows up like in LLVM, for example, or in the Julia assembly code if you take a look at it. So they've really like made sure to have like hardware support for fast floating point precision, and I would expect this trend to continue with newer architectures. We'll probably try to reduce this precision as much as possible, and just seeing like if you get any diminishing returns from it. So another like sort of similarly to batch normalization, if you're doing anything with gradient accumulation, where you're accumulating like a bunch of gradients before you apply them in one batch like together. Well, in this case as well, you need to basically make sure that you rescale your gradient updates. Otherwise, you're gonna either end up with them having too little input or a nan, and so that's definitely something you want to avoid. Uh, and that's pretty much it. So really, like the main takeaway that I want you to have is that if you want to port a model to mixed precision, generally all you need to do is basically make sure make sure that the model uses half precision, and make sure that your inputs are also half precision. The main thing you need to consider is that if you're getting nan or zero errors, it's very likely that you need to do loss rescaling, where you multiply by some sort of scaling factor and then scaling factor back after you do the weight update. If you don't want to worry about this, NVIDIA has tools with automatic mixed precision to make this really easy. And finally, I don't think that floating point 16 is sort of going to be the standard. Like I would expect people are going to experiment quite a bit with different exponent and significant sizes for various floating point representations. One of the reasons why these innovations may take a while to actually figure out is because it will take a while to like you can definitely figure out quickly whether you get a degradation of performance with different floating representations in software. But to figure out if you actually get substantial throughput improvements, you actually need to be able to run this on a real hardware, and that always takes more time. So that was it for this article. Sorry for this video. So I hope you enjoyed this, and if you have any other questions about mixed precision or tricks for making models run faster and more cheaply, feel free to let me know in the comment section below, and make sure to subscribe if you like this content. It makes it a lot easier for me to justify spending a lot more time on it. And thank you so much.